in the line of people from yesterday that's pretending to be somebody else, because Hjalte, who was the first author of this joint work, was going to give the presentation, but he was not able to come, so I'm replacing him instead. And I would like to take the talk from rainfall observations to, let's say, future precipitation. So we did comparisons of some different weather generators and tried to use them as input to an urban drainage model. So this is some joint work from DTU in Denmark and from Aalborg University. So the background is that there's been a lot of focus on climate change, and that, at least for Danish conditions, has focused very much on estimating extremes. So the publications here, primarily by Carsten Arnbjerg and his group of people, have concerned a lot on estimating climate factors for representing a future climate. And basically, those climate factors, or the result of this work, is the climate factors that depend on the return period and the duration, and can be applied for design of drainage systems and generally within urban hydrology. So basically, they estimate different climate factors for different return periods. But we know that it's not only the extremes that will change in the future. So in Denmark, we will have more winter precipitation. We will have changes between, or time between events. For example, drier summers, but larger single events. So the motivation for this is that we cannot use these climate factors if we have, for example, a design of an urban drainage systems where we have runoff dependent on the antecedent soil conditions. If we have, let's say, more complex drainage systems, if we have basins, storage volumes to fill up, combined to overflow volumes, that depends on a lot on, let's say, not only the extremes, but the variability over the year. Also impacts on wastewater treatment plants, real-time control, such, and that kind of problems. So there's a need to do some long continuous time series of rainfall representative for a given climate scenario. So we would like time series like this. This is a historical series that is projected into a climate projected series. So what have we been doing? We compared 4 different weather generators in order to test the performance, both for present climate and for future climate, in terms of modeling or long-term simulation of a drainage system response. So the different types of weather generators is one from 2009 by Christoph Onoff and Carsten Arnbjerg, 2 that Hjalte Sørup, who was going to give this talk, presented, and something that we did at Aalborg University. So we're trying to compare those weather generators, both in the present and the future climate. And then we compare against IDF curves and return periods related to the simulated response, so pipe capacity, surcharging, combined to overflow volumes, and some volume measurements that I will not go into here. So we use it for the present climate, so either with historical data or a replicate of historical data, and in a future climate projected to 2100. So the different weather generators, I'll not go into the details on how they actually work, but we have a reference which is 2 rain gauges representing the present conditions. And then we have the red one, Onoff and Arnbjerg, which is a Bartlett-Lewis pulse model, which is downscaled by a random cascade model using a climate scenario A2. And we have one for the present and one for the future conditions. And then the second one here is SERPs. Maybe I should say up here that it's downscaled from 24 hours to 1 minute values. SERP is a spatial Newman-Scott pulse model in 1 hour resolution using another climate scenario A1b, and we have 2 from the present climate and 2 for the future climate. And the third one is also Hjalte's, which is an empirical perturbation scheme based on observed series. So it's sort of a delta change method using a combination of 2 different climate scenarios. And that one don't have the present conditions because they're equal to the rainfall measurements from the tipping bucket. And then the one that I'm responsible for, it's a stochastic resampling of rain series where we use some random change factors to represent the future climate. And here we use a 1b scenario and have 1 or 2 from the present and 2 for the future climate. So we're generating a minimum of 30 years time series for each of these, and then select 10 years to do the analyses. So some of the challenges that you might question. With the weather generators use a different temporal resolution, so we have one generating with 1 minute values and 1 hourly. The regions are not totally the same, so we have some representing an average Danish conditions and the others use the local stations. We use different climate scenarios, which is a problem that I'll get back to. And the periods that we compare are not the same in all of the weather generators. And we project to 2100, but the length of the series differ. So it's not really fair to do a direct comparison of each of the generators. So we're focusing more on the applicability of the methods rather than comparing the actual outputs, as a sort of a disclaimer. So we use a case study area in Aarhus, Denmark, 2 catchments, a small one and a large one, where the small one is pretty flat and the large one is quite steep. And then we simulate this through a MikeUrban model, reference model. So some results. This plot here shows the present conditions, and this one the future conditions. And now we're looking at the seasonal precipitation, so the amount of millimeters per season. So we have spring, summer, autumn, and winter. And what you can see from the present conditions is that we have some variation from model to model. The observations are in gray and the other colors representing each of the weather generators. So there's a bit, the SO1 here, Hjalte model is under-predicting compared to the observations. Others both under and overestimate the seasonal precipitation. I think this one is representing the observations the best. That's also what I did. Oh, sorry. And the future conditions, we have for some of them an increase in the seasonal precipitation, some more than others, and this one predicts a little increase, but still quite a large variability between the models. This is the same, basically looking at the number of events rather than the seasonal precipitation, but still per season. And you still have a lot of variability it seems like all of them actually underpredicts in the number, in the present conditions, the number of events per season. And you have for some of the weather generators an increase depending on season, but still a large variability. The results, however, look somewhat better if you look at the IEF curves, and I think that's possibly because most of these weather generators have been optimized to actually produce the extreme statistics rather than the annual or seasonal statistics. So they are quite agreeing on that we should be here somewhere for the present conditions and somewhat larger for the future conditions. And this is for 1 year return periods, and this is for 5 years, and so we see a bit more variability, but still same tendencies. So then we're looking towards putting the data into a model. I think we have a rather good consistency. This is, or maybe I should say that this is the parts of full flowing pipes as a function of return period for present and for future climates. And I think we have a fairly good agreement between the different methods for the present climate, except for this green one here. And that's due to that we have 1 hour time steps. So the other ones are using 1 minute time steps. So when we look at full flowing pipes, this time step is really crucial. And obviously, as you can see also with the gray, it's 2 gauges located close to each other, but still we see some variability, so we should also take that in mind. The future climate doesn't change very much, and that's actually because a large part of the pipes are already full for 1 year return period, so we will not see an increase even though we increase the rainfall intensities. This is the same for the other catchments, somewhat same tendencies, I think, but a different response of the catchment. This is the number of CSOs. Here we see a minor influence of the temporal resolution as we did when we looked at the surcharging or the full flowing pipes. And those two here, the yellow and the green one, systematically predicts more overflow in the future climate. So that was also what we would expect to some extent. Yes, this is the CSO volumes. Basically the same as the number of CSOs per year. Hjalte, who did this plot, did it on a log axis, so it looks somewhat better, but still there's some variability depending on the model. So it's not really possible to see whether one is in this case better than the other. So we're trying to do this qualitative performance instead, ranging from 1+ to 5+, which is the best. And we're testing against some different, let's say, outputs from this. And the first one, ability to test the performance on the present climate. Well, 3 of these get a high score because we can actually produce what's representative for a present climate. But this one uses the original series, so it's not really possible to validate on the present climate. Then we have applications for small catchments. Well, the ones here, which is a perturbation of observed series, performs the best. Also for seasonal statistics and for full flowing pipes, because there the short time steps are important. For CSO frequency and volumes, there's equally performance of all of them. And then there's the last one, which is the data availability and the flexibility to actually use this. And I think this method here that Hjalte produced is quite easy to do, and it's just a simple perturbation of the observed series, whereas this one that we did requires a lot of stochastic simulations, so that one is, let's say, more computational heavy. So to conclude, it's difficult to compare results quantitatively since we have data based on different climate scenarios and different methods, and we're not actually comparing the same thing, so it's a little bit of apple and pears and bananas, I think. All weather generators that produce historical time series is useful, so we can use it actually to test the performance, even though we know that there's a large variability. And even at the hourly scale, when we look at combined sewer overflows, for example, it's okay to use an hourly time scale. And then there's some different effects on the two catchments that I didn't go much into here. But still we see the relative effects of different weather generators. So all in all, we published this this year in Water Science Technology. But all in all, it's a difficult comparison to do because we're not actually comparing the same, but at least an initial try to use what we currently have in Denmark. So thank you.
Søren, it looks like the best method that is coming out is your method, isn't it? And they go here.
Well, you can count the pluses here. I didn't do this on my own, but...
Well, in fact, I can tell you that in the meantime, we tried the method as well, also presented later today, and indeed, you're right, it's a very good method. But in the beginning, I was a bit skeptical because the method is based on resampling, and resampling has the disadvantage that if you go to the extremes, you might, in fact, how can I say, underestimate the extremes because you resample the same event several times again. It doesn't seem that your method has this disadvantage, so what is your secret?
Well, it's true that we have, let's say, a pool of events that we sample from, and then we sometimes sample the same event twice, or more than twice, and that obviously is evident when we look at the stream event statistics. We did discuss whether we should, let's say, when we draw an event from the pool of events, whether we should put it back in the bucket or we should leave it out. But actually, in this case, we're only looking at 10-year return periods. So I think we have somewhat better statistical representation of 10-year return periods events than the 30-year return periods event. So we would see that we have, let's say, some of the same events sampled more than once if we go to the very large return periods. Probably. But that's also something that we're working on now and maybe trying to, instead of just a total random sampling of events, maybe sampling in different groups or different categories of rainfall or return periods. Yes?
You can do this later because you're looking. It's a quick one.
No, I just wanted to point out that depending on what you look at, right? Because if you want to look into the really, really large infrastructure investments for the future, which involves tunnels in cities and so on, for CSO abatement and for avoidance and flooding, the spatial component of rainfall is crucial, and SO1 is the only one of those that has that.
Yeah, you're right. I didn't go into that because this was just a comparison of the point input to but you're right. You're right.